Welcome to today's Explainer. We're diving straight into something absolutely fundamental today, the geometry of circles. We're going to trace how our fascination with this specific shape evolved from just, observing the natural world around us, right down to the incredibly precise mathematical symmetries that make it all tick.
I mean, just take a look around, from raindrops rippling out on a puddle to the cross-sections of tree rings or the crazy intricate patterns inside a sunflower. The flawless circle is literally everywhere in nature. It really is no wonder ancient humans were so captivated by these repeating shapes. Nature essentially handed us the blueprint way before we had the math to actually describe it.
We look up, and there it is in the night sky, the full moon. It's a shape that's been capturing our collective attention since it was first scratched into ancient cave paintings in Odisha. Really, think about that for a second. For thousands of years, humanity has just stared up at the moon, recognizing that exact same unmistakable geometry we saw rippling in a pond. Even during something as dramatic as a total solar eclipse, we get this completely captivating, perfect outline just staring right back at us. It's almost begging to be understood. So it really pushes us to ask the big question: what are the specific rules that make this shape mathematically perfect? Okay, section 1, defining the circle and finding the center. Let's get right into it. So the crucial takeaway here is that mathematically, a circle isn't just a ring. It's actually defined as a set of points, a locus, on a two-dimensional plane, and every single one of those points is held at the exact same distance from a given center. It's simple, but it's elegant. Every dot on that boundary satisfies that one condition, being perfectly equidistant from the center. And of course, that distance, that's our radius. Now, because of that strict definition, a circle has complete rotational symmetry. Think of a spinning wheel. It looks exactly the same at all times. If you blink, you literally can't tell if it moved. It is flawlessly symmetrical. Plus, if you were to cut a circle out of a piece of paper and fold it exactly in half, that crease acts as a perfect line of reflection symmetry. It goes straight through the center, forming our diameter. Moving on to the next section, connecting the dots, drawing circles through points. Let's see what happens when we force this mathematically perfect shape through some specific points on a plane. I want you to actually think about this for a second. If I draw just two random points on a piece of paper, let's call them A and B, how many different circles do you think you can draw that pass through both of those exact points? Go ahead, take a mental guess. The answer is actually infinite. It's kind of mind-blowing. To draw a circle through A and B, your center point just has to be the exact same distance from both of them. So, mathematically speaking, any point lying on the perpendicular bisector of A and B works perfectly. Since that bisector line stretches on forever, you could draw incredibly tiny circles or massive planet-sized ones, and they'd all share those two specific points. All right, let's bump it up a level. What if we plot three distinct points that don't form a straight line? Three non-collinear points. How many circles can connect all three of those? Exactly one. There is a single, totally unique circle that passes through three non-collinear points. We call it the circumcircle. Basically, those 3 points form a triangle, and there is only one perfect circle in existence that can enclose or circumscribe that specific triangle. And finding it is actually pretty neat. By locating where the perpendicular bisectors of the triangle's sides intersect, we find that unique center, the circumcenter. And here's where it gets cool. Watch how it moves based on the triangle's angles. For an acute triangle, the circumcenter lives comfortably inside. But if it's an obtuse triangle, it actually falls completely outside the shape. And for a right-angled triangle, it lands perfectly, and I mean perfectly, on the midpoint of the hypotenuse. It's just beautifully precise. Okay, next up, section 3, the secrets of chords. We're looking at the hidden internal architecture now. So let's dive inside the circle itself and talk about chords. A chord is just a straight line connecting any 2 points on the circle's edge. This illustrates it brilliantly. If you tie a thread tightly across 2 points on a bicycle wheel to act as your chord, and then connect its ends to the center hub, it forms a specific angle right at the center. Now, rotate that wheel. The thread moves, sure, but its length stays exactly the same. Think about it like this. Imagine you're standing right at the center of a circle. You stretch your arms out to the edge, forming an angle, right? Your hands are marking the ends of a chord. Now, imagine the floor magically spins you around. As long as you keep your arms locked at that exact same angle, the distance between your hands isn't going anywhere. Neither is the length of that chord.
That little thought experiment actually perfectly proves a major theorem. Equal chords subtend equal angles at the center. Inversely, chords that subtend equal angles at the center are always equal in length. It's a flawless two-way street. Mathematically, it all boils down to basic triangle congruence, side, 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 inside angle side, but intuitively, it just makes absolute sense, doesn't it?
Furthermore, try this. Draw a chord, pinpoint its exact midpoint, and then draw a line connecting the circle's center right to that midpoint. Mathematically, that line will always, and I mean always, be perfectly perpendicular to the chord. You're basically splitting an isosceles triangle right down the middle, creating two perfect 90-degree angles. It's like this hidden internal framework of right angles tucked away inside every single curve. So we've journeyed from just, observing the moon all the way to mathematically proving circles through 1, 2, and 3 points. But as our source material provocatively teases, what happens when we try to force a fourth point onto that exact same circle? I'll tell you right now, not just any 4 points can share a circle. So what unique conditions actually make that possible? Well, that's the million-dollar question, isn't it? I'm going to leave you to ponder that puzzle until we explore the next chapter of geometry. Thanks for joining me today.